All right, example 11. In the last example, we looked at a collision between a photon and electron, but it was all in one dimension, right? It was only just a head-on collision going backwards and forwards. So in this problem, we're looking at a collision where the electron gets scattered off at an angle. So we're looking at a 2D collision. So let's draw a scenario, a diagram of what it looks like initially and finally. Okay, so in this case, we have a photon that has this particular wavelength. This is the initial wavelength. We'll call that just lambda, which is 0.03 nanometers. It's coming into this electron. It's a little bit off center, this electron. So this is my electron at rest, right? But it's slightly off center so that when it hits it, it goes off at an angle. And it's going off such that this angle here, call that theta, is 30 degrees. Okay, we are not given that angle phi. That's the angle that the reflected photon goes off, but it doesn't really matter in the end because we're solving for the shift in wavelength. I realize this is not initially, that is finally, and we are not given, for example, the speed of the electron. No, we're not. So we don't know that either. But from derivation, and I'm not going to go over that in this video, we could derive what's known as the Compton shift equation. Using the conservation of momentum in the x direction, that's the initial momentum in the x direction, and this is the momentum of the photon that's been reflected in the x direction, right? And then this is the momentum of the electron. And then this is the momentum along the y-axis. And then here, this is just conservation of energy. I would say out of these three equations, probably the most important one would be utilizing the energy formula. This is the energy of the incident photon, reflected photon, and the kinetic energy of the electron. The rest is a little bit trickier to derive, but using these three equations, you can algebraically manipulate them to get this equation right here, which is on your AP formula sheet. So that's what we're going to be utilizing. All you need to know is the angle, which we're given, the mass electron, the speed of light, and we're just looking for the shift in the wavelength. So we know that theta is 30 degrees, and we know that the original wavelength is 0.030 nanometers. And then there's some other information that we could look on our equation sheet, such as the mass of electron, 9.11 to the power negative 31 kilograms. The speed of light, which is 3 times 10 to the power of 8 meters per second. And then we can often go on to get part A. So part A is asking for the change in the wavelength of the photon. So I'll just write out the equation. The change in wavelength, and you're simply getting this from your equation sheet, right, is equal to Planck's constant divided by the mass electron times c, all right, and then 1 minus cosine theta in brackets. So we're just going to now just plug that into, plug in the numbers and then solve for it. So for the mass electron, it's 9.11 to the power negative 31 kilograms. Planck's constant is 6.63 to the power negative 34 joules seconds. Okay. That value, sorry, is actually up the top. It's getting late for me here. 6.63 to the power negative 34 joules seconds. Speed of light is 3 to the power of 8 meters per second. And then 1 minus cosine of 30 degrees. And we're just simply putting that into our calculator. And I get, when I put that all into my Desmos calculator, I get 3.25 to the power negative 13. Okay, the next part is asking to find out what is the wavelength of the scattered photon. So we're asked to find out this new wavelength. We'll call that lambda prime. Okay. I'll ask you first, is this wavelength a longer wavelength or a shorter wavelength? And think of it, E equals hc over lambda. Is the energy of the reflected photon going to be larger than the incident energy for the photon or smaller? We are coming to the conclusion that it will be smaller because some of this incident energy is going to be transferred to kinetic energy, the electron leaving less energy for this reflected photon. So the smaller the energy, the longer the wavelength. right? So the wavelength can be calculated, all right, for part B. We know that the shift in wavelength is going to be the longer wavelength, that's the wavelength in the end, minus the initial wavelength lambda. So if we want to find the shifted wavelength, we take the original wavelength and we add the change in lambda. So in this problem, we are told that the wavelength is 0.030 nanometers, and then the shifted wavelength is 3 to the power of negative 13 meters. Maybe we'll convert that to meters, nanometers. So in 1 nanometer, there is 1 times 10 to the power negative 9 meters. That gives you 3.25 to the power of negative 4 nanometers. Okay, so then we add that to this. That's 0.000325 nanometers. So our new wavelength is going to be 0.030, all right, 325 nanometers. We probably round this off to 0.303, but that's the new wavelength, maybe with all the digits here. Okay, almost done. C, what is the energy transfer to the electron in electron volts? Okay, we can't calculate the kinetic energy of this because we don't know the speed. But we do know the wavelength of it initially, and we do know the reflected energy of the photon at the end, so we can use conservation of energy. So for part C, the kinetic energy of the electron, or I guess you could just call it E of the electron, but it is basically kinetic energy, is equal to the change in energy of the photons, which is basically the energy of the photon initially minus the energy of the reflected photon finally. So this is going to be, how can we calculate that? We know we have lambda, so let's just use hc all over lambda minus hc all over lambda prime. Okay, or you could rewrite this as hc brackets 1 minus lambda minus 1 minus lambda prime. Okay, I am running out of room, so maybe I'll move this all over to there. And for the value for hc, since my wavelengths are in nanometers, I'm going to use the one with electron volts. So I'm going to use 1240 electron volts nanometers for hc all multiplied together. And then in the brackets here, I will have 1 minus the original wavelength, which is 0.03 nanometers, minus 1 all over 0.030325 nanometers. And this will calculate to be 443 electron volts. Okay, so I'm a little bit, have a typo here. This should be 0.443 kilo electron volts, because you want to convert it to kilo electron volts. Well, in 1 electron volt, in 1 kilo electron volts, you have 1,000 electron volts. And this gives you, 0.443 kilo electron volts. Okay, that's it for this example.